Okay, so this chapter is about sources of magnetic fields. We've talked about this. Where is that? Okay, so here are the Maxwell's equations. What are the Maxwell's equations tell you? The Maxwell's equations tell you? Well, so the way they're written, these are the causes and these are the effects. So what we're going to study is, what we've seen is moving charges produce magnetic fields, okay? And that's what we're going to see today. This equation, this is the Lorentz force equation, tells you how do you detect these fields. So if you want to detect an electric field, what you need is a charged particle. And if you want to detect a magnetic field, what you need is a moving charged particle. Okay. So again, like I said, there's a beautiful symmetry. Moving charges produce magnetic fields. And to detect magnetic fields, you need moving charges. Okay. All right. This is an electromagnetic gun, but we'll come to that in a second. Yeah. So this chapter is about moving charges producing magnetic fields. Okay. What we're dealing with, what we are studying is a subject called magnetostatics. What that means is, okay, so we are studying currents producing magnetic fields. The currents are not functions of time, they're steady currents. Okay, so they've been flowing, so everything will say applies to that. And then it'll turn out that even if the currents are changing, this change in time is small, then everything we say will apply. Okay. So here we go. So here's the basic formula. This is the basis for the whole chapter. So here's a charged particle. It's moving like that. We'll have it moving in a straight line. And this guy will produce a magnetic field all around him. Okay. Now, so we'll give you an expression that is effectively true. Okay, so you can't apply it to a single moving charge. What it'll apply to is there's an infinite number of moving charges, okay? And what is the effective contribution of this one charge? Okay, so that's that's what this is. Okay, so here's a moving charge. It's moving in a straight line, and there's the velocity. Okay, so now think of it. The charge is moving along the axis of a cylinder. Stick it, and this is a positive charge. Stick your thumb out in the direction of the motion, and your fingers point in the direction of the magnetic field. Okay, so there's the magnetic field. The magnetic field are tangent to the cylinder. Okay, and you could guess. Okay, the further out you are, what do you think will happen to the magnetic field? They would get weaker. Okay. So here's what this chart does. So when it's moving along the cylinder, it's producing fields like that. The fields get weaker as you go further apart, now further away. Now here's one thing, there's along axial points, this chart doesn't produce magnetic fields. So along the axis, the field is zero. Everywhere else, it's non-zero. Yep. So here's the magnetic field it produces. Okay. The magnetic field is given by mu naught divided by 4 pi. Mu naught is the vacuum permeability. It's a constant. Okay. And there's its value. Q is the charge. So if Q is 0, if a neutral particle is moving, then it's not producing a magnetic field. V cross R hat. V is that. R hat is a unit vector in the direction at which point you're trying to figure out the magnetic field. So R hat is a unit vector pointing at that point. We're trying to figure out the magnetic field at that point. And the strength of the field is inversely proportional to the distance squared. Okay, it's divided by R squared. All right, this is a cross product, V cross R. Here's the vector V, here's the vector R. And so the cross product is perpendicular to this plane. V cross R, if you turn a screw like that, the screw will come out in the plane like that. And so the magnetic field is pointing like that. So in this plane, the magnetic field is perpendicular to that. Okay. So again, so I'll draw a cylinder. Oops. You have a charged particle moving along the axis, and the magnetic field everywhere will be perpendicular to this cylinder. Okay. So stick your thumb out in the direction of this axis of the cylinder, and your fingers, use your right hand, your fingers point in the direction of the magnetic field. Okay. And that's the basis. Okay, so moving charges producing magnetic fields. Okay. Now, if you have a current, what is a current? What is a current? It's a bunch of moving charges. And so at any given point, what do? You find the field due to one charge, due to the other charge, and if they're all moving in the same direction, at that point they'll all produce fields in the same direction, and so the fields will all add up. Okay, so the field, so if you take a small element of the current, there's a bunch of charges moving here, and all these guys are producing a field coming out of the sheet like that, and they all add up. So the field due to all these guys, these charges moving, is again mu naught by 4 pi I times ds. ds is the small element cross r. So this right here contains the number of charges times the charge times their speed. That's what this contains. Okay, so see, that's that's the charge of each guy, the speed of each guy, and n, the number of charges in that volume, is contained in this expression. Okay. So that's the field produced at this point due to this element of the current. Okay. So what we have given you is the expression for the magnetic field produced by a single moving charge, and then the easy extension of, if you have a bunch of charges moving, there's the field produced by a bunch of charges moving at a given location. And with this, now you can build the field due to any current distribution. Okay. So let's say, all right. I don't have a diagram for that. Okay, so let's say you wanted to find, here's a current carrying conductor, you wanted to find the magnetic field at this point due to this current. Okay, so the magnetic field, so again, anytime you want to find the field due to an element, stick your thumb out in the direction of the element, and your fingers will point in the direction of the magnetic field. So if you extend this guy, the field due to this guy will be out of this paper sheet. Okay, it'll be coming out B. So, well, I'll indicate, remember, fields coming out are indicated like that. So the field is coming out of the sheet, and this will be dB. Okay. Now, if you want to find the field due to the entire current, all you have to do is integrate that. Okay. So there's the integral in principle, and for a wire like this integral is impossible to do. But there's the general expression. Okay. When can you do the integral? When can you find the total magnetic field due to this current? If this has a symmetry to it. So we can do this integral for an infinitely long straight wire, for instance. Okay. All right, so we'll do that. So again, this is the field produced uh, at that point due to this element of the current. R hat is that vector. Okay. Okay, so here's the general expression. Okay, so this is for a current distribution. Okay. Now this integral in general, like I said, it's impossible to do for a general current like this. But when the current is symmetric, has a symmetry to it, then you can do this integral. Okay. So for an infinitely long straight conductor, we can do this integral. Okay. And I'm not going to do the integral, but here's the answer. So the integral is for an infinitely long straight conductor. The magnetic field is concentric circles, and the magnitude at a distance r or distance a is given by mu naught I divided by 2 pi a. Okay. So, and if you use your right hand, you'll get the sense for the magnetic field. Okay, so the magnetic field is tangent in this direction, and the magnitude is given by that. And this expression was obtained by doing this integral for this infinitely long wire. Okay. All right, so what this chapter is about is, what are we studying? We are moving charges are producing magnetic fields. Okay. Again, if the particle were not charged, if Q were 0, the magnetic field wouldn't produce a magnetic field. If V were 0, B would be 0. Okay, so a moving charge, it is a moving charge that is producing a magnetic field. All right. And here's the general expression. And like I said, this integral can be only done for symmetric current distributions. And here's a simple case. An infinitely long wire for which the magnetic field is given by that. This moving charge, where does it not produce a magnetic field? Where? Along the axis. Okay. So it's not producing a magnetic field along all these points. So you got to remember that. Okay, now let me tell you about this this toy. It's pretty interesting. It's called an electromagnetic gun. And here's what it can do. So you can see that this device would fit in this room. Accelerations of 5 million Gs for a millisecond with launch speeds of 10 kilometers per second have been achieved. What does this mean? What happened? It's doing that again? No way. All right. I give up. All right. So accelerations of 5 million Gs. What does that mean?
5 million times the force of gravity.
Yeah, so this device, okay, so here's a Here's a view of this. Here's the payload. This device can exert a force 5 million times the weight of the object. Now, so what does that mean? So let's say your payload was your physics teacher. You apply a force of 5 million times the weight of the physics teacher. What you get out is a pellet. Okay, you apply a force 5 million times the weight of something, it would get crushed. So that better be a solid object. Okay. All right, how does it apply this such a large force? So, by the way, there's the payload. It applies this kind of force for about a millisecond, and it's coming out at 10 kilometers a second. What is the escape velocity from Earth? 11 kilometers a second. So it can launch stuff into space. Okay. So how does this work? Okay, so this is it's called a rail gun. Okay, electromagnetic rail gun. So these are metal rails. This is a fuse, and there's the projectile. Okay, so when you want to launch it, all you do is you flip a switch and pass a very large current through this thing. When you pass the current, this instantly vaporizes. Okay. The current, and there's a magnetic field, so there's a current flowing through like that. Okay. So we'll say there are positive charges, Q cross Q, V, and there's a magnetic field into the sheet. Okay. And the magnetic field can be produced by this current as well, so you don't need an external field. But anyway, so Q cross V. So V is in that direction, B into the field. On this field, on each of these charged particle is exerting a force in that direction, which is transferring that force to the payload. And you can exert a force 5 million times the weight of this thing. So it's absolutely amazing. Okay. All right, so this is the field of an infinitely long wire. It's concentric circles, okay, and the field gets weaker. It falls off as 1/r. Okay. Here's the field of a circular loop of wire carrying a current. Okay, so here's the magnetic field. So this is matte, and here's the magnetic field of a bar magnet. And you can see the magnetic fields are similar. This guy is called an electromagnet. A loop of wire carrying current is an electromagnet. And the advantage this has is you can vary the current, so you can vary the strength of this magnet. You can turn it off and on, and you can flip, you can flip its polarity by changing the direction of the current. So the magnetic field lines of this loop of wire and the bar magnet are similar. Okay. Here's the expression for the field of a loop of wire. So I need to find a new diagram for this. So there is R, there is Z. So here's the strength of the magnetic field along axial points. Okay. And again, so if the current is in this direction, the field on the axial point is, again, you stick your fingers in the direction of the current and your thumb points in the direction of the magnetic field. Okay? So the field along this point, at this axial point, is pointing in that direction, and that's the strength of the field. Mu naught times N, the number of turns of coil, I, the current, R is the radius of the coil, Z is this distance. Okay, now what we'll do is we'll multiply this by mu N I I r square, so 2 pi. I multiply that by pi and divide by pi. R square plus z square. 3. N is the number of turns of coil, I is the current, and pi r square is the area of the coil. This guy here is the strength of this magnet. So the strength of that electromagnet denoted by mu is N, the number of turns of coil, I times the area of the coil. And we'll associate a vector with the magnet. The magnet, what do magnets, a magnet is pointing, the strength of the magnetic moment of a magnet points from the south pole to the north pole. So for an electromagnet, you stick your fingers in the direction of the current and your thumb points in the direction of the magnet, okay? So that's the magnetic moment or the strength of the magnet. Okay, so for this expression, if Z is large compared to R, the magnitude of B is falling off as 1 over R. So if Z is large compared to R, this can be dropped. Then this would be Z to the power 3. And that's what this expression is. Okay? For large Z's, or in this case, we've named it X. For large X's, the magnetic field is falling off as 1 over X cubed. Okay. So what this expression is giving you is, so here is a current carrying ring, and the magnetic field along points far away compared to the size of the ring is falling off as 1 over X cubed. Here is the magnetic moment. The strength of the magnet is N times I times area. Okay. So a current carrying loop is a magnet. It's called an electromagnet, and it is very versatile, and we use it everywhere. Okay, so we use it in speakers and microphones and all kinds of stuff. Okay. Okay, what produces magnetic fields? What produces magnetic fields? Moving charges. How do you detect magnetic fields?
Moving charges.
With moving charges. All right, so let's do the following. Let's have 2 wires carrying currents. What is a current? Moving charges. Okay. So in this wire, you have moving charges. That'll produce magnetic fields. Where does it produce a magnetic field? Everywhere around it. Okay, so these guys produced a field everywhere around it. And this wire carrying a current has moving charges. So these moving charges must feel this field. So anytime you have 2 current carrying conductors, they must interact. Okay, this guy is producing a field all around it, and that field is felt by these moving charges. Okay, so it turns out that when two conductors are carrying currents parallel to each other like that, those conductors attract each other. And when the currents are in opposite direction, they'll repel each other. Okay. Now, of course, this expression is when they're parallel like that. This expression won't apply, for instance. So this expression applies for 2 infinitely long wires like that. It wouldn't apply for this configuration or that configuration. Okay. So this is a very special configuration. All right, so the force, what this expression says is the force per unit length is mu naught times I1, I2 divided by 2 pi A. Okay, again, when the currents are parallel, the force is attractive, and when the currents are anti-parallel, the force is repulsive. If one of the currents is 0, okay, if this current is 0, well, this guy is producing a magnetic field, but there's no moving charges to feel it. Okay, so both the currents have to be non-zero for you to feel, for this force to be non-zero. Okay, so the next thing we'll talk about is Ampere's law. Now this is similar to, let me remind you of Gauss's law. You guys might remember Gauss's law when we had electric fields. The flux through an enclosed surface, which was E dot dA, this surface integral was equal to the charge inside divided by epsilon naught. Okay, that was Gauss's law. Gauss's law said this surface integral, okay, you did that for an enclosed surface. So this was a surface that was in 3 dimensions, was equal to charge inside divided by epsilon naught. For this is a similar expression, except that now this is a line integral. So if you take the line integral of this magnetic field around a closed loop, if you take this line integral, that line integral is equal to mu naught times the current that is threading this loop. So if you're taking the line integral in this sense, then the current in this sense is positive. Again, you're using your right hand. If your fingers are going in the direction of the line integral, your thumb points in the direction of positive currents. Okay. So if you're doing the line integral in that sense, that is the direction of the positive current. If you're doing the line integral in this sense, then that is the positive direction for line integrals. Okay. Anyway, so Ampere's law relates the line integral of the magnetic field along a boundary to the current being threaded inside. Okay. So again, this kind of stuff is useful in calculating currents in certain configurations. Okay. But that's sort of the parallel of Gauss's law for electric fields. Yeah, so here's an example, but we won't worry about that. So so let's say you have a very thick wire like this. What this is showing you is, there's a current flowing in the wire, and the dots mean the current is coming out of the sheet. And what this diagram shows you is, see, at the center, again, let's go back to this expression. See, a current carrying like this is producing a magnetic field, concentric circular magnetic field. Now, if this wire were thick, what we are showing you is that there's a field inside the wire as well. Okay, and it's in the same sense. It's in concentric circles. Okay, once you're outside the wire, the magnetic field, the strength of the magnetic field is falling as you go further and further. So this is showing you the strength of the magnetic field inside the wire. So here's this wire, here's a cross section of the wire, and they're showing you the current density is uniform. The current is coming out of the sheet. The magnetic field at the center is 0, and as you go further and further out, the strength of the magnetic field is increasing. The strength of the magnetic field is strongest at the surface of the wire, and once you go outside the wire, the strength of the magnetic field it's falling off. Okay, and that's what this is showing you. And this can be proved. So these expressions can be derived using this law, Ampere's law. Now we produce magnetic fields. We various configurations of magnetic fields for different applications. So here's a configuration of a magnetic field that is useful in something called a tevatron, a tokamak, which is a fusion reactor. So hopefully, well, fusion reactors have the promise of unlimited supply of energy. Okay. Do you guys remember what? So let's say if you have a magnetic field like this, and if I take a positive charge and throw it like that. So, for instance, in this room, there's a magnetic field. North is in that direction. There's a magnetic field pointing in this direction, and I take a proton and throw it like this. What will happen? It'll wrap around the field lines, right? Okay. If I throw it perpendicular, it'll just go in circles like that. If I throw it at an angle, it'll spiral around it like that. Now, if this field were straight or it ended, then when the field ends, the proton would escape. But what if I want to trap the proton? I don't want it escaping. What can I do? If you made the field a loop, then it would, so if the field were a loop, then it would just wrap around like that. Okay, so there you go. And so here's a field that is a loop. And the way to produce that is you go buy donuts, strap wires around the donuts, and pass a current through the donut, and what you have is a field in a loop. Okay. And now the charged particles will just wrap around them. Okay. And look at this. You can have these charged particles at billions of degrees, and they're not even hitting the wall. Okay. And hopefully some of them will hit each other and fuse. Okay? And that's the fusion reactor. And that's what this is. See? So here's a tokamak. And you can see this. Here's the plasma that's probably at hundreds of millions to billions of degrees. Okay? And what happens is in these tokamaks. So here is a one that has not been fired yet. Here is the size. I don't know. Okay. So there is the plasma. There's no person for size here. Okay. Well, roughly these guys probably are roughly. So this chamber is about the size of this room. Okay. All right, so the idea would be the following. So I'm going to draw the magnetic field like this. So the magnetic field is going into the sheet. A proton going like that will feel a force. This will wrap around in a circle like that. And another proton coming around like this. Hopefully these two guys will collide and fuse. Okay. So that's the idea. All right, so circular loops of magnetic field are useful in the tokamak, and this expression gives you the strength of the magnetic field. Mu naught N is the number of turns of wire per unit length. And if you want to make a strong field, you just wrap around more and more wires. Okay. What else can you do to make a strong field? So here's why you need a strong field. The hotter the temperature, the faster the particles are moving. The stronger the field has to be to make them go in a smaller circle, okay, to trap them. So the hotter the gas you want, the stronger the field you want. All right, so to make a strong field, you get the number of turns high. What else can you do to make a strong field?
Increase the current.
Increase the current. What do you need to do to increase the current? The more current you have, in ordinary wires, it turns into heat. All that energy gets wasted. You need superconducting wires. Okay, so you have superconducting wires. So you have wires wrapped around that thing, and they're superconducting wires, and you have a high density of wires. So the stronger the field here it is, the hotter this gas can be. Okay, the hotter the gas, the higher the energy yield, the more fusion reaction can happen. Okay. All right, so here's a configuration where you have a uniform magnetic field. This is a solenoid, so what this is a cross section of a cylindrical object, okay, a cylinder, and you wrap wire around it, okay, and again superconducting wires, and you'll have a strong uniform field inside this thing. Okay, again the expression, the strength of the magnetic field is the same, mu naught n, the number of wires per unit length, times I. Do you guys remember where do you need fields like this? In MRI machines you have field like this. Okay. In the Large Hadron Collider, so look at that. So this guy is packed with particle detectors, and this guy has a uniform field like that. And what happens is, so there is where the beams come in. Two beams, proton beams come and collide, and they produce particle-antiparticle pairs. So there's this detector. So at UF, there are people who make detectors that pack this volume. All right, so at CERN, these beams come and collide there, and then a whole bunch of mess is created here. Okay. So a particle-antiparticle pair, let's say an electron and positron. Okay. So the magnetic field is in this direction. Okay. So this is a positive charge. V cross B would be a force in this direction. So V cross B would be a force into the sheet. This guy would curve in that direction. V cross B would be a force in this direction. That guy will also curve in that direction. So if you have a particle-antiparticle pair, they both curve in that direction. And you can see that. So at the center, here is a particle-antiparticle pair. Okay. So this fella Okay, so there's the current Large Hadron Collider, and that's where the detector is. Okay, so you can see this detector. Okay. Um, so that detector, this is packed with detectors, particle detectors, and the entire volume has a strong uniform field which can be produced like that. Okay. All right, so here are particle antiparticle trajectories. Okay. And this is a proton-proton collision, and it's not as messy. Look at this. This is a gold nucleus colliding, and you have a mess that you have to be that has to be analyzed. Okay, now I'll briefly go over magnetic materials. What produces magnetic fields?
Moving.
I'm sorry.
Moving charges.
Moving charges produce magnetic fields. Okay, atoms are filled with electrons. Electrons are charged particles, and they're moving, and so they should produce magnetic fields. Okay, so a simple model is, okay, so here's a nucleus. Okay. And this is n equal to 1 orbital, n equal to 2 orbital, n equal to 3 orbitals, and so on. That's the quantum number, and the n refers to the angular momentum is nh bar. Okay. Okay, that's this. So that was Bohr's model. Okay, so here's an electron going around. Okay, and so the magnetic moment of this electron going around is I, the current times the area, and so when you apply quantum mechanics, there is the result. For these quantum numbers, for n, for each quantum number, L can take values from 0 to n minus 1. L equal to 0 is the s orbital, L equal to 1 is the p orbital, that's what you remember in chemistry, and L equal to 2 is d, and so on, the orbitals. Okay. So that's the L quantum number. Okay. So the s orbital, L equal to 0, L is 0 for s orbital. For s orbitals, the electrons are going back and forth like that, so they don't have any orbital angular momentum. Okay. But in a p orbital, so again, simplistically, here's electrons going around, and they behave like a magnet, and there's the magnet is pointing in this direction because they're negatively charged particle. Okay. And the strength of this magnet, okay, so in an atom, each electron circles the nuclei once in 10 to the minus 16 seconds. So that's how fast they're going around. This would produce a current of 1.6 milliamp and a magnetic field of 20 Tesla at the center of the circular path. So a single electron going around in an atom should produce a field of 20 Tesla. Is that a strong field? That's a very strong field. So what's going on? How come you don't feel it? So in general, when for every electron going around like that, there's an electron going in the opposite direction. Okay. What about for an odd number of electron atoms? Half the atoms are odd number of electrons. So the last odd number, the odd atom, it's in a s orbital, so it has no orbital angular moment. Okay. So the orbital angular momentum essentially gives you zero field. In most materials, because of oppositely moving electrons, magnetic effects is either zero or very small. Okay. But there is one effect that doesn't cancel. Okay. Any moving charge produces magnetic field. So an electron can go around in circles, and that effect is canceled. but each electron is spinning as well. So the spin produces a magnetic moment. Okay, so here's an electron spinning, and the magnetic moment is in the opposite direction because it's a negatively charged particle. And here's the strength of this magnet, of a spinning electron. So the spinning electron, there's the magnet, the strength of the magnet. And this is called Bohr magneton after Mr. Bohr. And the strength of this magnetic moment is that 9.3 times 10 to the minus 24. The units are joules per Tesla. Okay. Look at this. So this is magnetic moments of some atoms and ions. The magnetic moment, by the way, so here's an electron that is spinning. Is a proton spinning? Does a proton spin? A proton also spins, and its angular momentum is also the same, except that the strength of the proton's magnetic moment, see, the mass of the proton is 2,000 times that of the electron. So the magnetic moment of the proton, spinning proton, is 2,000 times weaker. Okay. So if this guy is in play, then we won't worry about the moment of the proton. All right, so here's a hydrogen atom. A hydrogen atom is this guy. The orbital momentum is in s orbital, so the orbital is sort of going like that. That doesn't contribute, but it has a spin. So the moment of this should be the moment of the spin of the electron plus the spin of the proton. But this guy is negligible compared to that. So the magnetic moment of the hydrogen atom is that of the electron spin. See exactly this value. Okay. For the helium, the magnetic moment is 0 because for every electron, there's an oppositely paired electron. Okay. For all the noble gases, the magnetic moment is 0. Okay. Okay, I'm going to quickly go over these slides. Just briefly mention them. Okay, so from a magnetic perspective, you can classify materials into 3 kinds: paramagnetic, ferromagnetic, and diamagnetic. Okay. These guys, both paramagnetic and ferromagnetic, the atoms are magnetic, or there are electrons that align that. Atoms are magnetic, okay, so we'll keep it simple. In a diamagnetic material, the atoms are not magnetic, but if you put them in a magnetic field, they acquire a magnetism in the opposite direction. Okay, so as far as everyday things is concerned, these guys you can make strong magnets out of. You can't make permanent magnets out of these. These guys are anti-magnetics. You can think of them in that way. Okay. So when you go buy a magnet at a store, it's a ferromagnetic material. Okay. In a paramagnetic material, each atom is, you can think of this as magnetic, but you see, they're not cooperating. Okay, they're not interacting strongly enough. In a ferromagnetic material, nearby atoms interact strongly and they align themselves. Okay. In an antiferromagnetic material, this is the 4th time. So these are other subclasses. We won't worry about that. So in a ferromagnetic material, they cooperate and you can make them all align together. So here's a ferromagnetic material. This is the size of a grain of sand. And this thing has about 10 to the 20 atoms. See, all those magnets, each of those atom which is a magnet is all aligned in this domain. But this bulk sample, it's not magnetized because they're all randomly aligned. So if you want to make a strong magnet out of them, you got to align them. How do you align them?
With the magnet?
What's that?
With the magnet?
So what you can do is you can wrap wires around them like that, pass a strong current, which will produce a magnetic field and align them. Okay. So if you apply a strong magnetic field, you can align them. Okay. And this can be demagnetized by heating it and so on. Okay, but you can align them by passing a strong current. Right. So there's something we define called a magnetic moment. Magnetic moment, remember, the strength of a magnet is equal to the magnetic moment. So the magnetic moment is the magnetic moment per unit volume of a substance. So if you have some magnetic material, it has got a bunch of magnets. And what is the magnetic moment per unit volume? That is denoted by M. Okay. This is the external magnetic field you apply. And so if you do material science, this is the notation that is useful there. So this is field strength. Field strength is B naught is equal to mu naught times H. Okay, so this is defined like so. This field strength has the same unit as magnetic moment per unit volume. All right, we won't worry about that. So I just want to mention paramagnetic substances have small but positive magnetic susceptibilities because of atoms with permanent moments. These atomic moments are weakly interacting and in the absence of external fields are randomly oriented. That means this diagram. Okay. So they're randomly oriented. They do not interact strongly enough to influence each other and align, like in a ferromagnetic material. Diamagnetism. Okay, so if a material is diamagnetic, let's say you bring a magnet around like that. You produce a magnetic field, you bring a magnetic field close to it. This, in a diamagnetic material, you induce an opposite magnetism. The magnetic moment induced is in the opposite direction. So, if you introduce a magnetic field near a diamagnetic material, you'll repel it. And water is diamagnetic. So in this experiment, water is diamagnetic, and what they show is, so what they do is they freeze this frog, so it doesn't run away when you do the experiment, and it's levitated in a field of 16 Tesla field. So you introduce the 16 Tesla field, and the diamagnetism produces a repulsive force, and this frog has been levitated. And that's what happens here as well. Here is a superconducting magnet, okay, and an ordinary magnet is, this is this is the superconducting magnet, and here's an ordinary magnet, and its superconductor is perfectly diamagnetic, and the repulsive force is making it float. Yeah.